Hello and welcome back to Calculus 3 section 14.3 on motion in space. So the flight of the bug would have a path. That path will be described by the vector valued function r. That bug will be going at a certain velocity, which would be the r prime, right? The derivative of position is velocity. The magnitude of that vector would be the speed. It's how fast the bug is moving. And then we can also take another derivative to get the second derivative of r, which would be acceleration. Then there is a third derivative, which calculates jerk, which you can experience in your car when you slam on either the gas pedal or the brakes very quickly. You know that, so jerk is the change of acceleration. Your gas pedal and brake pedal are both accelerators because one accelerates, the other one decelerates. So those are both acceleration, one positive, one negative. They're both adjusting the velocity, right? So velocity is the one that changes your position, so you can get places, and acceleration is the one that changes your velocity. So both gas pedal and brake are acceleration. Now, if you press those two harshly, either one of those, you experience jerk, which would be the third derivative. There is more, but it's already too much, and jerk is even not mentioned in the book. So as you are going through these layers for motion in space, we are first going to think of the path, right? Which would be denoted as s of t in most of the applications, but we use r of t as our vector because we want to use the r of t as our function, and we can use our regular vector of x of t, y of t, and z of t. So our position, well, path, or let's change it to position, whatever. Path, position, whatever you want to call it. So that's our position vector, and that's just a vector that points from 0, 0, right, origin. Whether you are in 2D or 3D, it points from the origin to the point in space where the whatever is moving, whatever that thing is. The next one is velocity. And velocity as v of t, it's a vector, is going to be the derivative of r of t. We covered the derivatives last class, so you know that you are just supposed to take independent derivatives of each of the components, and you are done with that. Now, speed. Speed is going to be the magnitude of the velocity vector. So speed is the square root of x prime squared plus y prime squared plus z prime of t squared. All these are of t. So this is our velocity, this is our speed as just the magnitude of the velocity. And then finally we have acceleration, which would be a of t, again as a vector, and that's going to be the double prime of r of t, which is x double prime of t, y double prime of t, and z double prime of t. So what you are doing here are the derivatives of independent, right, derivatives of three components. So you are doing calc 1, 3 calc 1 problems in each one of these. So that is our motion in space. And now if you have something given, whether it's 2D or 3D, if it's a 2D, you will ignore all the z components. If it's a 3D, you will obviously include all of the z's. So if you take R2 case, circle, radius, let's say 4, whatever, you will have immediately parametrization for that as r equals 4 cosine t 4 sine t. So in R2, circle of radius 4 is given by by this. So now what you can do is you can quickly come up with the velocity vector. Velocity vector would be the derivative of this, so negative 4 sine t 4 cosine t. So that's the velocity vector. And acceleration vector would be negative 4 cosine t negative 4 sine t. We also can calculate the speed. We can do it here on the side. So speed would be the magnitude of velocity. We only have two components to deal with. So we only have to do x prime squared plus y prime squared. It's from velocity. So we have a square root of 16 sine squared t plus 16 cosine squared t, which is equal to, you factor out 16, so it's a square root of 16 times 1, because sine squared plus cosine squared is 1, and you get that the speed is 4. So if the position is given in, let's say, meters, then this would be 4 meters per second on the speed. So for the circle or radius 4, so now if you want to take a look at the graph real quick, you will be able to put together some of the motion that we talked about in the counterclockwise and all of that. So I'm not going to put any of those counterclockwise motion or anything. I'm just going to take a look at the position. So let's call the position orange. So I'll put the orange star there. And I will put the position vectors going from the origin into these points around the circle. So the black line, the circumference of the circle, is where the, I don't know, maybe bug is flying in a, no, let's do the illegal thing. It's you just going in circles on a circle. I'd say that's it, right? You know, the traffic circles, the death traps. You're just driving around. It's actually a ticket if the cop sees you doing that, but just so you know. And you shouldn't be doing it because of the death trap, as I said, but anyway. So going from the center to any location at the circumference, you are talking about, right, position. So that's orange star. Now you have your velocity. Velocity is going to be tangential to the motion. And if you carefully calculate velocity at, let's say, t equals 0, which is on the x-axis, right? T equals 0 on the x-axis. For t equals 0, you will see that first component is 0 and the second component is 4. So velocity vector, which is our blue, or should I do red? Let's do red. Velocity component is going to go like this. Now, if you draw the vector and calculate vector and draw a vector at every single one of these, you see that these vectors are trying to spin the circle counterclockwise, which is why the orientation, when you have a cosine first and a sine second for your parametrization, is counterclockwise. So you see that these velocity vectors, the red ones, right, are trying to spin the circle counterclockwise. You also see that it's tangential to the position, which is why on a curved road like this, right? When a car is coming in and there is a smudge of oil, leaves, and water, and whatever else, smudge of water, oil, leaves, and it's frozen at the same time. All right, how about that? If the car runs into this, it will tangentially go off the road, right? It can't continue because there is no grip between tires and the road, so there's no friction for the car to stay on the pavement, and because it slid on this goo of things. So it would go off the road tangential to the curvature of the road, which is the tangent line at that point. So we see that on our circle with all of these red lines, the velocity is always tangential to the motion. Finally, with the blue, we have our good friend acceleration, and you will see that acceleration is completely opposite from the position, which means acceleration vectors are pushing in. So acceleration vectors are from every point you would think anywhere on the, you can draw these acceleration vectors anywhere. They will always, all of them will be pointing towards the middle. So the same for this car. The car has the path, which is again some kind of orange position in terms of the center of the circle for the curve. Then you have the red tangential, which is the velocity, and then finally you have the, no, I have this backwards. The supposed to go, no, I had it right. Goes this way, and then the blue one would go that way. There we go. So that will be the car on the road. Some tires on the ends right there. Look at that. Perfect. Now it doesn't matter what kind of problem you get. Clearly, next one should be, let's say, helix, because that's the next best thing. Say you have a predator bird that flies around and then just goes whee and swoops some kind of unfortunate soul on the bottom. So you can come up with the equation for that if you know what is the radius for this bird to fly, and then obviously observing the t as it descends. So it's going to be actually a negative t because it's going to go downwards. So we might have the position over here. Now this is going to be 3D obviously, so we're going to have all components. I don't know, 50 feet. So 50 cosine t, 50 sine t, and then let's say negative 3t or whatever going down. So this is your position vector for this bird of prey coming down as in a helix path, on a helix path. And then you can calculate the velocity very quickly by taking independent derivatives, which is negative 50 sine t, positive 50 cosine t, and then negative 3. And then finally, the acceleration of the bird, negative 50 cosine t, negative 50 sine t, and 0 on a z-axis. So now we can also calculate the velocity of that bird by figuring out the negative 50 sine t squared plus 50 cosine t squared plus negative 3 squared, and that will give us, when we square this, we get 50 squared and then another 50 squared, and then sine and cosine will give us 1. So 50 squared plus 9. 50 squared is 25 with 2 zeros, and then you add 9. You have a square root of that. So it's going to be 50 and something a little bit more So you see that there is no difference in calculating a 2D case or a 3D case. If you have a vector valued function, can be in any dimensional space, which means that you have this motion. Now, you also have the circular motion in here with the sine and cosine. And what we also have seen earlier, we saw that the velocity was perpendicular to the position, and then acceleration was perpendicular to velocity, which means their dot products would be all zero. And that's placed in a theorem 14.2, motion with a constant r, where it says that in conclusion, then r dot v would be equal to 0 because these are orthogonal. So if you have anything traveling on top of the sphere, let's say you have a basketball sitting on a ground somewhere, you have an ant walking on it, right? The acceleration vector is perpendicular to velocity. Velocity is perpendicular to it's just because it's on the curved surface. So the sphere will have the same features as a circle, except it's going to be in a 3D. So all of that stuff is orthogonal. Now, you have to be also careful what you claim when you are working on surfaces that are not flat. You see, the flat surfaces, like the floor over here, the parking lot outside, and for the most part, I mean, if you take a piece of land, it does appear flat. So you have these morons thinking that the earth is flat. It's a medical term. Why are you saying? It's that particular range of IQ. Well, it used to be. Now they're all retards. But anyway. Well, it's medical terms. I can't avoid it. So when you are on a flat surface, the shortest distance between 2 points is the straight line. And that's called Euclidean space, Euclidean distance, and you have the shortest way. But when you are on a curved surface, the shortest distance is not the straight line. It's longer that way because of the curvature of the space you're in, the curvature on the surface you're in, bumps out, right? So if you go straight, you actually have to battle that bump. But if you go in a curved space, in a curved line, you are not going over the bump as much. You're going a little bit to the side, so it's actually shorter. So if you are on a plane of any kind, so we're talking about surface of the desk or the floor or the parking lot, whatever, you have a point A, you have a point B, yes, straight line, shortest distance. However, if you have a planet, and the planet is round, it's a ball, because basic physics, and you are going from point A to point B, right? You have the North Pole over here and the South Pole on the bottom. The shortest distance between this on the curved space is this, what we call geodesiac, which is a line that you get when you draw the plane between two destination points, say New York and London. You want to fly to London, or actually, the hell with London. Let's pick a better place on the planet. Pretty much anywhere else. How about Spain? Spain's awesome. So you want to go to Spain, right? So you have New York, you have Madrid, let's say, and the center of the Earth. So you would put the plane through these 3 points. That would actually create this kind of triangle-looking thing, right? And this plane would actually intersect the surface of the Earth and would create the line. And now, because it's obviously angled from the center to go to these 2 points, that plane would cut through the surface of the Earth, and it would create what we call the geodesiac, which is the shortest distance between 2 planes on the curvature. Now, you can, guys, actually do this on a basketball or anything else If to observe any path of the airplane across Atlantic or anywhere else, you will always see them go in a curve rather than straight. Obviously, if they go straight, they're not going to have enough fuel. They're going to run out of fuel and then it's going to crash into the ocean. They have to take the shortest path, and the shortest path is always the geodesic. The geometry on the surfaces that are curved is not the same as the geometry that you guys are used to on the flat surface. What's the sum of all angles in a triangle? Yeah, it's 180 degrees, but only on the flat surface. That doesn't hold on curved surfaces. If you are to draw a triangle on your forehead, right, where it curves right here, it's not going to be sum of all angles is 180. And it's very easy also. You can measure that on your basketball at home. If you have a ball, we can talk about the planet again. Maybe some of those imbeciles are watching this so they can hear it for the third time that the planet is round. So here we have a North Pole on the top. And let's say you start at the North Pole and you walk straight down to the equator. You're going to hit the equator, right? And then you are going to turn 90 degrees to walk on the equator for exactly a quarter of the circumference around the Earth, a quarter of the equator. And when you walk a quarter, you're going to turn 90 degrees and you're going to walk up to the North Pole. So clearly you already have 90 plus 90 is 180. There is still another angle on the top, right, to add to this triangle. Remember, all of these are straight lines. Equator is a straight line when you look at it sideways. Each one of these is a straight line when you look at it sideways. So if you walk in a straight fashion, directly north to south, straight, you will hit the equator halfway between north and the south, and then you turn 90 degrees, walk around the equator, 90 degrees, you walk up. So what's happening now, if you take a look at a top view of the planet, take a look at the top view, you are going to see that you, from the North Pole, you walked straight down to the equator, then you walked quarter of the Earth's, and then you walked up. So what is the angle at the top? Also 90 degrees. So this is also 90 degrees. So what's the sum on the triangle? What's the sum of the angles in a triangle that is on the surface of the ball? It's 270, right? It's not 180. Now, if you have a cereal bowl, right? If you have a cereal bowl that is round, and you draw a triangle inside, the lines that appear to be straight drawn will appear curved like that. All of the angles would be adding to less than 180. So the curvature of space, the curvature on top of these shapes that are not flat, gives us different geometry, and some of the stuff is really not intuitive, like parallel lines intersect in the curved space. That's the feature that you don't have in a flat space, right? Two parallel lines never intersect on a flat surface. So when you lay a train tracks on top, those are parallel and they never meet. Yeah, but the train tracks are on the flat surface. You would put them on the floor right here, and you would have them go forever, and they would be parallel, and they would never intersect. All of these lines are parallel. And they meet at the North Pole, and they meet at the South Pole. So they do intersect on the curved surface. They are parallel. They are parallel. They are intersecting at the same time. So if you are interested in mathematics, if you want to learn all of these kind of things, you will look up hyperbolic surfaces. You will learn mathematics of hyperbolic surfaces, and then you will be able to eventually learn general theory of relativity, because it is built on top of hyperbolic mathematics, hyperbolic surfaces. Now, we have seen some of those. You saw the hyperbolic paraboloid, the settle thing, right? Now, also the top of the sphere, and then the ellipsoid, and all of the other ones that are curved. The geometry on top of those surfaces is not the same as the flat geometry you guys are used to so far. Now, we're not going to do anything in those systems in Calc 3, right? Because it's still, this is still elementary course in mathematics, so we don't deal with that kind of stuff. But it's at least good to know that these things are interesting. So now, knowing these facts, it's important to understand that this actually has a lot of use, because you are not going to have a straight line every time when you're going from point A to point B. In some instances, the shortest distance between 2 points is going to be a curved line if you are on the curved surface. So clearly, there is a huge benefit to knowing vector-valued functions. And then, obviously, Calculus 1 on 3 different components will give us 3 different derivatives to go into velocity, to go into acceleration. So that's the little talk about making sure you're getting from point A to point B in the most efficient way. So now that we are, oh, by the way, the other thing is that if you considered leaving the classroom, right, I don't think that anyone, like if you, let's say you're leaving, you had to ask me a question after the class, so you're standing right here next to my desk, and you asked your question after the class and you want to leave. Well, you have 2 options. The shortest distance is to climb over those tables, right? But that's not the least amount of energy, because now you have to climb up, right? So you get the idea? You will walk down this aisle and then make a right. So those are the things that you have to consider. Obviously, when you are going from one street to another, you do not jump or climb over the building. That's Spider-Man. You guys walk around it, right, as mortals. Good. Now, to find, we saw that you take derivatives, right, to go from position into velocity into acceleration. To go backwards, if you have acceleration, you will use integration, and then you have to mess with that plus c calculation we had at the end of the class yesterday to calculate the velocity for c, because constant c, because constant c is either initial velocity or is initial acceleration or initial position. So it's going to be something like that. Now, the one-dimensional motion, that you covered this in one-dimensional motion in Calculus 1, where you said that your acceleration is change of velocity in time, and then you work on a separable differential equation where you say that dv is equal to a dt. And now if a is, let's say, gravity, you want to do, let's say, the free fall, let's say, you can keep acceleration there. It's okay. But you can also plug in g if you want to work on a free fall. Should I keep acceleration? Yeah, I can keep acceleration. We can do the general form. You can always plug in g later. All right, let's just keep a. So a dt, and when you integrate both sides, right, so this is called the separable differential equations. A is just a number, acceleration of 7 meters per second squared. So when you integrate this, you will get that the velocity is equal to at plus some constant c. And this equation you probably have seen in physics if you took, even though this is basic physics now, where final velocity was equal to initial velocity plus acceleration times time, that c turned into initial velocity, v0. So mathematics would give you an equation that looks like this, and then physics would just rename all of the variables and give the subscripts and so on, so it's easy to connect to the everyday dealings. So the physics will say that the final velocity is equal to initial velocity plus whatever change you give it with the acceleration. Now, if you are at a red light, your car is parked, I hope, right, waiting for the green. When the green comes up, well, your initial velocity is 0 because you were standing still. Your car is not going to go anywhere until you push the gas pedal for it to change acceleration in order to create the final velocity at which you are driving. So let's say it's a city driving, and your goal is to accelerate up to 30 miles per hour, and but you are at the red light at 0 miles per hour here. So you have to accelerate through time. You have to keep your gas pedal pressed until the velocity changes from 0 to 30, and then you will release it and keep it at 30 as you drive. Let's say that's the speed limit. So in order for velocity to change from 0 to whatever, 30 miles per hour, you have to have this acceleration term that in time will change one velocity to another. Also, you need time to brake, which is the reason why through residential area you are going to have 25 miles per hour. Let's say it's a straight street. Let's say it's wide enough. There is no reason for speed limit not to be 80, right? Fine. You don't have sharp turns, you don't have, right? But it's a residential area. Kids might be playing, the ball might be, going onto the street. The thing is that when you decelerate, which is pressing your brakes, it takes time to stop, right? You don't play games with a train. Trains cannot stop, maybe even for a mile, depending on how heavy, how many cars they have, and so on. So you don't casually park on the railroad crossing, right? And you see the train coming and say, yeah, they'll stop, right? No, they won't. So acceleration, again, both ways, either to accelerate from one point to another, right? You want to get a Tesla Model S with a ludicrous button on it. Yeah, it's going to cost you 100K, but hey, you get to accelerate in 2.3 seconds, right? Which is the fastest we have now on the planet. For the cars that are driving around. But the braking works the same way. It has to take time to decelerate, which means to change your speed from 60 down to 0. It takes much longer than to change your speed from 25 down to 0. So if you're driving 25, you see a ball enter the road in front of you, you can stop much faster than if you're driving 60. So acceleration with time will change velocity either up or down depending which pedal you press. It's either gas or a brake. By the way, if your car has a third pedal on, it's time to move on and upgrade, okay? Because we at least moved on in efficiency to 2 pedals. All right, good.
I have 2 pedals.
Yeah, you can upgrade. It's cheaper on everything. Cheaper on gas, cheaper on insurance, and
no fun though. It's no fun though.
I don't follow.
Like it's not as fun as 3 pedals.
Okay. I will say you win in that case. And finally, the differential equation to determine position if you have velocity. Let's say you have a velocity function given. So velocity is change in position in time. So if you have this given to you, you can again say that change in position is equal to velocity times dt, which is again separation of variables, and you put position on one side and you put the time on the other, integrate both sides, and here is your position function, which would be velocity times time plus some constant c. Now you immediately go to, oh, hold on. Velocity is given as at plus v0. That's the part that I missed. So now you're integrating equation for velocity, and you will get that the s of t, right, the position function, is equal to acceleration times time squared over 2 plus v0 t plus some constant c. And then you will, in general, find this in your physics books as y equals negative 1/2 g t squared plus v0 t plus y0, which is generally for free fall. Now, I did tell you earlier that we can keep the acceleration, or we can put the gravity if you are talking about something that is in the free fall. So the equation that you probably were dreading to memorize, well, actually, I don't think you memorize anything else in physics. They just give you formulas now. The whole thing is pointless. But clearly the equation came from a very simple mathematical integral there, where you just integrated the formula above. And this equation has all of the components that you need in order to either throw something the distance or just the simple oops of dropping something to the ground. So if you also observe the form of this equation, you all should be able to spot the negative t squared, right? So this equation is a quadratic equation because you have negative t squared, and in the middle you have a t term, right? So that is clearly negative t squared is a negative quadratic, the parabola that opens downwards. Now, if you ever thrown a rock into the river or anything ever, you always observe that type of behavior. So no matter which way you throw, right, unless you are a professional baseball player and you're supposed to throw the ball, go really crazy way, but no matter what you throw, as you can see, it creates this parabolic motion to fall. And anything you drop, it will go straight down. Now, the difference is this vector here, the vector v0, and that vector v0 is the vector at which you launch the object. If you drop something, that is just a pure y component going down, right, for velocity. It starts at 0, you just dropped something, so this term actually doesn't even exist. It's 0 if you drop something, right, because if I hold this bottle in my hand, its velocity is 0, right? When I let go, it will start picking up velocity because it will accelerate due to gravity, right? So when I let go, right, at the moment I let go, the velocity was 0. So if I am to work this equation out, I need to have y0. This y0 compared to the floor, let's say floor is the reference point, y0 would be 4 feet up, right? My v0 would be 0 because there is no initial velocity. The difference when you can say that, you know, someone dropped something or someone is angry is exactly the v0 part, right? Because there is a difference between the two motions, which is number one, whoop, which is straight down when you drop something, or you get, come on, right? The two different, right? This motion gave the v0. The only difference between the two, right, they have the same motion going straight down, right? It's the same eraser, same object, same mass. The whole thing is the same, except one was oops, and the other one was slam, right? So the difference between dropping or throwing an object. Now, you can also throw the object up, in which case the vector v0 will have x and y components to it because you launch something forward in the x direction and in the y. So if you observe carefully the motion at which I throw, I mean, clearly, if you observe a 2-year-old throw, then you can question the laws of physics because I have no clue. Every time they throw, something ends up behind them. But if you have never seen that? Never seen a kid go, right? And just, I had to practice that because it takes a lot of skill to actually get it, to release like in a right time as you are trying. It's impeccable timing. But for us, right, normal people, when you throw something forward, you should go forward. And when you throw something, right, as I throw like this, you see that my hand is not moving just forward, it's not moving just up, it's moving in this motion like that, which gives the angle with the floor, right? So it will have x and y component, it will some kind of a vector that will be there, and then you get to propel the object and throw it forward. The cool fact to know is that the furthest distance, right, in terms of the range you achieve as you throw objects at 45 degrees. So that's the furthest you can throw an object. If you are having a contest with your buddy to, throw a snowball over the river to the other side, if you're able to master a 45-degree throw, you will have much better chances of making it to the other side than using just a pure muscle to do it. So, thinking about physics and thinking about all of these things, you have all these derivations. They are absolutely the same as in Calculus 1. And now the Calculus 3 allows us to just stuff all of these equations into two vectors rather than have them scattered over the concepts and all these kind of things. Calculus 3 just gives you the chance to kind of pack everything into these two equations. So, summary, this is page 888. For the summary, for the two-dimensional motion in gravitational field, so R2 motion in gravitational field is going to be consider an object moving in a plane with a horizontal x and a vertical y-axis subject to force of gravity. So we are talking about like that. You have x-axis, y-axis, you have this v0 vector to shoot an object straight. So given the initial velocity vector, initial velocity vector v of 0, which is when the motion starts, to be u0, v0. So these are your x and the y component. One is u and the other one is v. And the initial position vector r of 0. Oh, I forgot the arrows up there. You got to put the arrow. Which will be given as x0 and y0. So we come up with this formula where velocity in terms of time is given as a vector valued function of x prime of t, y prime of t. Well, we had this earlier, same thing. Now we're just going to put in the gravitational equation that we figured out up there. So u0, and we have negative gt plus v0. So this is the equation which we obtained earlier when I did, here. That's this equation when you change a with a negative g, right? When we use negative g because gravity, it's wrong to say gravity pulls down, but gravity pulls down, okay? It's wrong to say it, but there you go. So that's the velocity vector. Position vector r of t would be given by x of t, y of t, which is what we discovered earlier. And now we have our good old u0 t plus x0 for the position on x-axis, and the y-axis is the negative 1/2 gt squared plus v0 t plus y0, which is the equation I just derived a second ago. Again, I hope you haven't learned anything new, because these things are studied in Calc 1 and they are studied in both type of physics, whether you do the basic one or the engineering one. All of these concepts were covered many times, and now we'll just use Calc 3 to stuff all of this in a single vector. So you have your velocity in x direction. Guys, this is very important. When you throw something, only the y component of the velocity changes. The x component of the velocity is constant at all times. In order to change the horizontal, right, you will have to have something propel right, like a rocket or something, to propel the projectile that you threw. So when you're talking about the velocity, you can see that only the y component of the velocity is changing, where the x component is constant. And then when you go to the path, obviously you are covering distance in because you threw the object, right? The object will be covering distance, so the distance will have a variable in it to change in time. And then obviously the height would be changing as a parabola, because the object is first going up and then falling. Now, if you drop object, then the x components don't matter, because there will be no x motion. The object only goes straight down. For dropping, v0 is 0. So your velocity will only be what gravity ends up giving to the object. And then the position will be calculated without, again, v0 term, because if you drop the object, v0 is 0. We already discussed that. For the max height, this is the last thing we're going to mention here. So for the max height of the object, you will set the negative gt plus v0 equal to 0, because we know to find maximum, we set first derivative equal to 0, right? Well, the first derivative of a position is velocity. If you are looking for the vertical, which is the maximum, well, that will happen when the velocity y component is equal to 0. Why? Well, velocity is equal to 0 at the maximum because the object stops to change its direction to come down, right? Anytime you throw something up in the air, like I used to toss those erasers, the object will go up, and then the velocity will be decreasing because the gravity times t will be decreasing the speed. And then the object will stop at the maximum height and then start coming back down. Now, obviously, you can beat this if you are using something that will, if you're using escape velocity, right? Because gravity for every object is a finite value, and if you propel the object or shoot the object sufficiently fast, which is greater than the escape velocity, then the object will not come back due to gravity, because gravity would not be strong enough to counter the effects. Now you have to invoke another equation in order for that, so on. So if you're interested in that, we can talk after the class. But all two objects that have mass, right, will be attracted to each other through gravity, and then if there is escape velocity, the force of attraction between two objects will be negligent, because it falls with the square of the distance, and there will be not enough time for it to. So there's all cool talk about that. So we can discuss that later if you're interested. And that's it. So we took all of the concepts you knew from before. We reviewed the derivation for them, and we just stuffed them into these vectors, vector-valued functions. To find the max height, you have v0, you have a gt. G. You will find the time at which it happens, and then you plug that time. So let me just go like this. So this will give us time t. So that's number one. Number two, plug t into r of t to get max height on y coordinate. So that's like a little roadmap of what happens. So if you need to calculate max height, when you set the y velocity to 0, it will give you the time. So let's say 3 seconds. Then you take that 3 and you plug it into negative 1/2 gt squared. So it will be negative 1/2 g3 squared plus v0 times 3. And since you have all of those numbers, you can calculate. That's it. Bye.